Hey everyone. I think I'm audible. Let me know if you guys can hear me properly and if I'm audible. Able to solve minimum platform to bubble behavior. Able to solve. Uh, Audible and visible. Awesome. Uh, Shubham Babbar Bhaiya will be not be joining today. I think he will join next week. Okay, so yeah, today we'll be discussing, but we'll try to see like how to solve the problems. We'll try to solve it. Cool. Okay, so how did the contest go? How were the problems overall? Like, did you guys like the problem? Did you guys not like the problem? Were they difficult? Were they easy? How do you feel about like how was it overall? Inputs were wrong for minimum platform. Okay, I'll take a look. Second problem solved only. Okay, cool. Yeah, so we have three problems. Like the problem. Cool. We have three problems. Let's start with the first problem. Okay, so the first problem is subtree in a n-ary tree, right? So we are given the root of a n-ary tree. Zero problem solved. Some values were greater than 2, 3, 5, 9. Okay, okay. Given the roots of a n-ary tree, find the number of duplicate subtree in the n-ary tree. So two trees are duplicate if they have the same structure with the same node values, right? So basically what it tells is you are given a tree. N-ary tree means it's a normal tree, it's not a binary tree. Generally we are given questions on binary trees, but if it is written only tree, then you have to assume it's a n-ary tree, right? N-ary tree means each node can have up to n child nodes, any number of child nodes, be it 0, 1, 2, 3, any number of child nodes. So you are given a n-ary tree, you have to tell two trees are duplicate if they have the same node values and the same structure, right? So yeah, like we'll discuss about what a duplicate is. So what we have to find is given the root, you have to find the number of duplicate subtree. You have to find the number of duplicate subtrees, and we'll discuss about it. So here, if you see 4, 4 is duplicate, right? It is duplicate. Then 3, 3 is also duplicate. Yeah, so these are duplicate. So again, the answer will be 2. There are two subtrees which are duplicate. All right, that's there. But one more thing. Yeah, we'll discuss it in an example like what exactly duplicate is. In this case, there are no duplicates, right? If you see there are no duplicates here, so that's why it is 0. So you're given n is 10 to the power 3, right? N is 10 to the power 3, and the node values are also within the range of 10 to the power 3. So you have to find you have to find the duplicates. Cool. uh, yeah, so that's the question. How can we solve this, right? Let's understand that. Okay, sorry. Yeah. Okay. uh, in the example note, what about other 4 under node 2? How is that not a duplicate? Okay, other 4 under node 2, 3, 3, that is also a duplicate, right? But again, you will be pairing up duplicates. If you think about it, this 4 comes first, so this is not a duplicate. After that, this 4 comes in, so this is a duplicate. Okay, you are saying that this 4, the count is wrong. This should be a duplicate as well. Number of subtrees in the duplicate subtree in the inherit tree, and the same node value. Yes, so this should be a duplicate as well. Yeah, it should be 3, and in fact if we give the input we should get 3. I'm not sure if the code is wrong or correct, but let's see. If we give this input right, we should get 3. Let's run this. Okay, what is the input format? Let's see. First of all, you are given n only one line input which contains the inherit tree in the form of label order. Example like this. So if I give it like this, 1 n 2 3, yeah, I'm just copying this only, right? Why is this not working? Oh, it will run against my code, so that's why I don't have a code. Anyways, yeah, that's, I think it's because 2 4 is treated as one subtree. No, it is not treated as one subtree. 2 is not mapping here, right? It is 4, the subtree of 4 that is getting mapped. So yes, you are right, it should be 3. It should not be 2, it should be 3. One thing can be as it is getting mapped to 4, right? Okay, I think I got the idea. No, so what is happening here is, as it is getting mapped to 4, this is also the same thing, right? All these 3 are the same thing. So it is not said how many nodes are duplicate, it is said that how many duplicates are there, right? Find the number of duplicate subtrees. So again, I'm not sure, but this should be or not should be, but if this is 2, in that case we will not consider 4 3 times, right? So if there is a match, we'll add the contribution of that match only once. Yes, I think that might be the case, that not unique count of pairs, but it might be the case that as all these three, 4 4 and 4 are the same thing, so it is being treated as one duplicate. Like 4 has duplicates, like that it is being treated, and 3 3 are the same thing, so 3 has duplicates. It is being treated like that. So that might be one case. Otherwise, the input output is wrong, right? So we'll try to write the code and we'll figure it out like what exactly is happening. But let's understand overall how to solve this problem. Okay, so actually, I have to adjust again. Just give me a second. Yeah, cool. Okay, so, and let's get rid of this. Yeah. So we have let's consider an example, right? Let's say we have a tree like this: 1 2 3 4, and again we have another tree of the same structure: 1 2 3 4. In this case, these two are duplicates, right? If you see, these two are duplicates. These two are duplicates. Cool. So let's understand with respect to subtree what do we mean. So 1 2 3, let's say we have 4 here, and we have 2 here, and 3 here, and 1 here, and we have 5 here, we have 2 here, we have 3 here, we have 1 here, and here we have 6 2 3 1, something like this, right? So in this case, if you see this subtree, right, 2 3 1 2 3 1 2 3 1 2 3 1. Okay, actually this should also be 2, otherwise it doesn't work. So 2. Okay, so if you see, this subtree and this subtree is the duplicate, right? This subtree and this subtree is a duplicate. Similarly, this subtree and this subtree is also a duplicate. 2 1 2 1 is also a duplicate. 2 3, this no, so 2 3, no, this subtree will not be treated, this subtree will be treated as a whole. So not 2 3, my bad. Yeah, 2 is here and 3 is here. So this is a subtree. This 2 1 is a subtree. This 2 2 3 1 3, this is a subtree, right? Similarly, this subtree is same as 2 2 1 3, and this 2 1 is same as 2 1. So these are the duplicates, right? But we cannot tell 2 3 is a subtree, right? Because 2 3 is not a subtree. 2 3 is just an edge. The subtree of 2 is the entire thing. So we cannot actually map them. We cannot treat them as duplicates. So that's why it will not work here. 2 1, here we have 2 1. Actually this will also not work because we have 2 3 1 as the subtree. So 2 1 will not be mapping to this 2 1, right? So that's the idea. We have to find the number of duplicates, right, in the subtrees. So how do we do this? Let's understand that. Okay, so let's think about it like this. How can we say, okay, let's just take two trees, right? 1 2 3 1. Can we say, how can we say that these two, how can we say that these two are equal? How can we say that these two are equal? One obvious answer of you will be, hey, let's start a DFS. What about 1 to 1? Yeah, those will also be there. The leaf nodes will definitely be there. I didn't consider the leaf nodes. I just considered bigger ones because leaf nodes you already know they will be there. Like this one will also be duplicate definitely. Okay, so 1 1. How can we know that these two are equal? So one solution that we will suggest is, hey, we do a DFS, right? 1 1, it's same. So we'll now recurse to the left subtree here as well and left subtree here as well. Or left child here, left child here. So 2 2, same. So we'll recurse to the left child here, the left child here. 1 1, they are same. So we see that there is no child. So we'll return true. We'll return true, right? Now we'll try to go to the right child, but right child is not there for both of them. So we'll return true again. So this means that this entire subtree 2 1 and 2 1 is same. Similarly, we'll recurse to the right child, we'll recurse to the right child, and we'll see that they are also same, and we'll return true from here as well, right? True from here. So both of them are returning true, and these values also matching. So we'll tell true. These two are identical. That's one way to tell that two subtrees are identical. We will do something similar, but we cannot actually do we can do that, but again it will be a brute force approach, right? Going through all the subtrees and then running a DFS in all other subtrees, trying to run a DFS with all other subtrees and checking whether they are equal. That will become a brute force solution. So we'll not we'll directly do some try to do some optimization. Okay, let's think about it like this. We have 1 2 3 1. Can we represent this in some way? Can we represent this in some way so that the value at pi, just looking at the value at 1, we can say what is the representation of the subtree. So every tree will have a unique in-order traversal. Every tree will have a unique in-order traversal. So what we can do is we can do a in-order traversal of it, right? In-order or pre-order or anything, right? So let's say we do a in-order traversal. So it will become something like 1. And after, let's say after every node value, we give $1. So $1. After that, we'll have, or rather, we'll do left, right, something like that. So 1. After that, 2, and then 1. Maybe 2, 1. Then L, because 1 is in the left child. Yes, we are trying to convert this. We are trying to convert the in-order traversal to some representation so that it can uniquely identify this. It can uniquely identify this structure, right? It can uniquely identify. Again, we cannot just write them like this 1 2 1 2 1 3, because 1 2 1 3 can represent a lot of things. 1 2 1 3 can represent a lot of things because we need two type of traversals like in order. Yes, if we are doing it like that, we need two type of traversals, but I'm trying to maintain the structure as well, if that is possible. Again, here we know that's true. If do we need two type of traversal, let me think about it. Okay, so anyways, let's try to reduce that. If needed, we'll maintain two strings, right? In order string and the post order string, and we'll try to do it from there. But anyways, I think that's true for the fact when you do not know the left or the right child. Here we'll also maintain that fact, right? That's the idea. Here we'll also maintain the fact which is the left child, which is the right child. And we cannot tell. So when we have two traversals, in order and post order, in that case we just have the values, the order in which the values appear. We do not have the direction as well. Here we will try to maintain the direction as well. So one traversal will only do, like one of them, maintaining one of them will only do. And again, I'm explaining that only 1 2 1 3 will represent a lot of lot of them, right? So it can be 1 2 and then 1 and 3. It can be like this as well, 1 2 1 3. This is one of the ways. Also it will not have in order, pre-order, post order like that, right? Because again, in order, pre-order, post order are kind of valid for binary trees. This is a n-ary tree. Although our example is binary, this is a n-ary tree. So we'll call it a DFS order traversal, right? A DFS order. So we'll try to do a DFS order traversal and maintain this that. So how do we do it? Let's think about it a bit. So we'll try to do a DFS order traversal and uniquely represent it as a string. Okay, so one, let's take an example, 1 2 3 4 5. Okay, let's do a DFS order traversal. So we'll start with 1. 1. After that we go to 2. Can we just represent it like that as an Euler tour, 1 2 5, and another tree can also have the same thing, right? 1 2, and here they can have 5. So that will not work. So we have to figure out a way to tell that this is of this thing. So 1 2. Okay, let's write it down, the DFS order 1 2 5 3 4. But 1 2 5 3 4 can actually belong to 1 2 5 3 4 can also belong to like 1 2, and here we have 5 3 5 under that 3 and 4. Like this also will have the same DFS order traversal, 1 2 5 3 4. Okay, so that becomes interesting. How do we maintain? Like we definitely have to maintain in a way. But how do we maintain? That is that would be interesting. So let's think about it a bit. 1 2 3 1 2 5 3 4. We have to make this unique, right? So what we can do is, instead, what if we do like this? Instead of that, what if we do a proper Euler tour? That is 1. When we come out, we also add it, right? So 1 2. After that we'll have 5. Now we are coming out of 5, so we'll also add 5 again. Now we are coming out of 2, so we'll add 2 again. Now we are going to 3. Now we are coming out of 3, so we'll add 3 again. We are going to 4 now. We are coming out of 4, then we are coming out of 1. Does this uniquely represent a tree? Let's understand that. 1 2. So 2 is one of the child nodes. So under subtree of 1, we know that 2 will come in. Okay, one of the child nodes. Then we have 5. Under subtree of 2, there will be 5. Now we have 5 again, so we are coming back to 2. We'll recurse back to 2. We can represent null with n also. We do not have null. We do not have null, right? This is not a binary tree. We do not have null. Okay. So 2. After that we are coming 2. So 2 will again return back. Then we have 3. So we'll explore the sub. Now we'll go to a new child 3 for 1 because 1 has not ended yet. Then we will have again 3. So we're coming out of 3. Then we have 4. Then we are coming out of 4. Then we have coming out of 1. So that will represent. But again, another challenge can be, let's say there are 2 3s like this, or 2 3s or 3 3s like this. So we do not know at this 3 whether to come out or like, although they will have a different representation. Anyways, they will have a different, like if we have another 3 after this, there will be a different representation for it, right? It will not be the same. So this way, like if we add when we enter in the string, if we add when we enter as well as we add when we get out of it, that represents us tree uniquely. That will represent the tree uniquely, right? Does this make sense? If we add when we enter as well as add when we remove, when we move out of the node, that is we are starting with 1, then so 1 is inserted now in the string. Now we are going to 2, so 2 is getting added to the string. Now we are going to 5, so 5 is, we can add n when we are at leaf. We can add n when we are at leaf. Why do we want to add n when we are at leaf? Then we are coming to 5. Okay, we are adding 5. Then we are again exiting from 5, so we are coming out of 5. Then we have 2, so we are coming into so we are going out of 2. Then we have 3, so we are coming into 3. Then we have another 3, we are going out of 3. Then we are coming at 4, so we have 4. We are going out of 4, we have 4 again. We are going out of 1, so we have 1 again, right? So that will be this will be a representation, right? And it will be, I think it will be unique. Let me know if it is not. So this way we can represent a subtree. Now the problem is very simple, right? Given a subtree, we know its representation. Given a subtree, we know its representation. Could you explain again how we know the second type 5 means? If we have a child node, let's think about it like this. Again, we are not trying to construct back the tree, right? We just want to make sure that it does not have the same structure. So 1, 2, 3, 4. What was there after this? 5, right? Just think about it. What if there is another child node with 5, right? Another child node with 5, what will be the representation? 1, we again, when we are entering, we are adding. We are entering 2, so we'll add 2. We are entering 5, we will add 5. We are entering 5 again, we'll add 5. We are going out of this 5, so we'll add 5 again. We are going out of this 5, we will add 5 again. We are going out of 2, we'll add 2 again. We are coming to 3, we'll add 3. We are going out of 3, we'll add 3. We are coming to 4, we are adding 4. Going out of 4, adding 4. Going out of 1, adding 1. This will be the representation if there is another child. If you remove this, think about the representation now. It will be 1, 2, 5, 5, 2, 3, 3, 4, 4, 1. These two are different, right? These two are different. So that tells us we do not need to construct it back. Rishit, we do not need to construct it back. We just need to make sure that these two are different. These two are different, right? So that is ensured. So now give it for every node, we are not doing in order. Vasant, we are not doing in order. In order is valid when? In order is valid, or in order, pre-order, post-order. These are valid only for binary trees. What we are doing is a DFS order. There is no more concept of null node or left is null, right is null, left, right. No concept of these things anymore, because we have a NRE tree. So we are doing a DFS order. Yes, we just want a unique representation. So that's how we can do. So for each node, for each node, we know the unique representation of the subtree. Now we can just store these unique representations in a hash map. So we have a hash map where we will store this representation as plus plus. Now whenever we see, whichever values has a frequency greater than 1, they will be the answer. If that's the case, if we just want to see how many of the representations are unique, or how many of the representations have a duplicate, we'll just add it when the count becomes 2. Only in that case we'll add, not 3, 4. But if we want the total number of duplicates, every time it is available, we'll just add it to the count. So in that case it will become 3, like for our example where there were 3 4s. There were 3 4s and 2 3s. In that case, sorry, not 3, 2 3. Yes, it will be 3, right? So we can just maintain this hash map. Okay, let's try to write the code for this, right? So I hope this is clear. Let me know if this is not clear with anyone. Okay, we'll make a method called okay, first of all we'll have to maintain the map, right? So let's call it a unordered map string, and maybe integer of frequency, or maybe boolean as well will do. is present, right? So what we'll do is string DFS. So string DFS because uh, okay, let's look into the code and we'll try to understand from there. So string DFS means what? String DFS is it will return the representation of this node, the current node that we are at. So we are at a node. It will return the representation, the string representation of the subtree of this node, right? String representation of the subtree of this node. So Sanyam, we are just what we are doing is we just have to tell that two subtrees are equal or not. That is, in short, we have to tell that two trees like 1 2 3 4 1. Let's say we have to tell that whether this is equals to 1 2 1 2 1 3 4, right? We just have to tell whether these two trees are equal or not. So what we have decided is we have decided that we'll maintain a representation. We'll try to maintain a representation of both of them, and using that representation, a string representation, and using those representation we can compare if they're equal or not. How do we maintain the representation so they become unique? What we'll do is we will add to the string whenever we in a DFS, when we enter it, we'll add to the string. When we go out of the DFS, how does DFS work? You enter one, from here you enter two, you enter one again, then you go out of one because one is explored, right? So that is how, yeah, that is how DFS works. So we enter when we start with one, so our string will contain one at the first. Now from one we go to two, in the DFS. So when we enter two, we'll add two to our string. Then we come to one, we will add one to our string. Now we are going out of one, we are recursing back to 2, so we'll add 1 to the string again. The second time also we'll have to add, otherwise it will not work. Then we have explored 2 completely, we are going out of 2, we will add 2 again. Now we'll come back to 1, from 1 we will go to 3, so we'll add 3. We are coming out of 3 again, so we'll add 3. We are going to 4, we'll add 4. We are coming out of 4 again, we'll add 4. We are coming out of 1, we'll add 1. This is a simple DFS order traversal I'm doing, and this is the representation. Let's see if this is same as this. So this representation will be, we are starting with 1. We are going from 1 to 2, so 2 will be added. We are going from 2 to 1, so 1 will be added. We are coming back to 2, so 1 will be added again. Now we have completed 2, so we will go back to 1, so 2 will be added again. We are going to 3 from here, so we'll add 3. From 3 we are going to 4, we'll add 4. We are coming out of 4, so we'll add 4. We are coming out of 3, so we'll add 3. We are coming out of 1, so we'll add 1. Are these two strings the same? The answer is no, these two strings are not same. So we'll say that this tree is not equals to this tree. Yes, going in and going out, yes. Can we add negative numbers? Is the number set negative as well? We can, it's a string, we can do that, but yeah, number set is not negative, right? So we don't have to worry about negative numbers. And we don't have, don't use negative numbers and these things, just add it again, that will work. You do not have to use, you can use if you want, you can use, but you don't have to do it. You can use the plus minus as well, but that's not really needed, right? So this should be enough. Okay, so let's so we are at the current node. So what we'll do is we'll construct the string representation for it. So string representation will first contain the current of data, and there will be the toString method will convert this to string, toString current of data, right? It will be an integer, we'll convert it to string. So first thing it will contain is this. Now we will go to all the child nodes, right? We'll go to all the child nodes. Let's see how is it given to us, how is the representation given to us. Let's come here. Yeah, so we have node, and then what we have, size is 0, add new node, parent key equals to null, node equals to new, parent key of children dot pushback. So we have children as well, right? Okay, we have children as well. So let's go to the children. So what we'll do is we'll go through all the child nodes for okay, and it is of type node. uh Children is of type node start. Okay, awesome. So we'll just do a loop on the node child belongs to current of children. We'll go through all the child nodes, right? We'll go through all the child nodes. What we'll do at the yes, to check the substrate enable. So what we'll do here is yeah, what we can do here is we'll dfs on the child node, dfs child. Now dfs child, from the child node what we'll get the child representation. From the child we'll get the child representation, right? So we'll just add the current representation to it. So representation plus equals to child representation. So if we will just append whatever the child representation is, we'll just append it to what is the current representation. So let's say we have 1 and after that we have 2, the subtree of 2. Just think about it again. Let's say we have 1 and we have 2 and 3 here. So at 1 we will have the representation initially to be 1. Now we go to 2 and 3. What will be the representation? What will they return? They will return 2 3 3 2. This is their representation. So we will get this. So we'll just add this to it, to us, 2 3 2 3 3 2, and after that we'll just append it with 1 once all the child nodes are over. So that's what exactly what we are doing. We are appending it, and finally representation plus equals to again to string current of data. Now at every node we'll just check if is present representation equals to false. If it is false, we'll also maintain the answer here, int answer. If it is false, we'll do answer plus plus, and is present representation equals to true. We'll just mark it to be true. So that will make sure that one representation, if it is repeated multiple times, if it is duplicated, a representation is duplicated multiple times, we will just count it one time as per the test case. But we'll see, like if this is not true, we'll just increment it every time it is yeah, sorry, is present is true, answer plus plus. That will actually not work. We have to maintain it as a count, right? So is present representation is equals to 1. In that case, is representation equals to 2, and count plus plus, sorry, answer plus plus, or rather representation, this is present representation will first increase the count plus plus. If is present representation equals to 2, answer plus plus, right? So answer plus plus, and finally we'll return the representation. So that should be it. So what we'll do here is we'll call the DFS from the root. Definitely we have to clear the answer, is present dot clear, and answer equals to 0, and we have to return here answer. So that should be the code, return answer. Let's compile and run this. So we are getting 1 here. Let's test against the custom input, that is this one. So whether it's 2 or 3, we'll understand from here only. So we are getting 2, expected is also 2, so that should be fine. Let's try to submit this. Yeah, so this works. So basically the idea was that idea is simple, but here the question was basically that if 4 is repeated multiple, if a representation is repeated multiple times, you just have to tell that this is a duplicate representation. You don't have to count it every time. Like here 4 was represented multiple times, right? So you just have to tell that 4 is repeated. So you have to count only one time 4 because it is repeated, right? So that is how this will work. Pretty simple code, but again the logic is very nice. Like you can represent an entire subtree in the form of a string, right? Cool. Let's go to the second problem. Again, I think this is a problem that I've solved in the similar problem I've solved in the last class as well, last interview series. So maybe we'll not write the code for this. I'm not sure. You're saying that the test case is wrong, so we might want to check that as well. But yeah, I was hoping not to write the code for this and let you do it as a homework. Right. So let's see. Okay. So you are in Geek. So also, like, if you know, if there is any test case which is wrong that you know, then you can let me know. We can just check it. But again, like, this is a problem that we have solved multiple times. So and last week we have solved multiple problems of this type as well, like ranges. So I would like you to write the code for this. But in case you know that it is failing for some test case which you think it should not fail, in that case, let me know that test case and we'll do a dry run as well, right? And we'll see like if this works or not. So you are in railway station. You are given a train schedule as follows. Arrival time array contains the arrival time of each station. Help with this, okay. Arrival time array contains the arrival time of each train. Definitely we'll discuss the idea. We'll discuss the how to do it. We'll write some pseudocode, but final solution we'll see. Like if you want to write first counter, yeah, we'll discuss the concept, right? But again, for the code, I would recommend you to try it yourself because this is a very standard problem as well. Okay, so arrival time array contains the arrival time of each train. Departure time array contains the departure time for each train. Day array contains the particular day when the train runs. Also, each train arrives and departs on the same day. Okay, you are given number of platforms. You are also given number of platforms that you have. You have to tell if it is possible to run all the trains with the given number of platforms such that no train has to wait. Okay, yeah, don't worry, we'll discuss it. So if two trains arrive and depart on the same time on the same day and the same platform, then depart the train first and then second train arrives. So basically it is just this last line is just saying that, let's say the arrival time of one train is equals to the departure time of another train. In that case, you can actually accommodate them in the same platform, right? That is, the first train will depart and then the second train will come in. So if basically if the end time of one train, the departure time of one train matches the arrival time of another train, then you can have them in the same platform, right? And if okay, we'll discuss about that. So we have 900, 940 like this, and the days are also given. So you have to output, platforms are also given. You have to output true, that is, it is possible to accommodate them, right? Cool. That is the question. And 2359 departure times. And why is it 2359? Because 2359 means 2359. If you think about it, 2359 means 11:59 p.m. Right? So after that, it becomes the next day. So it will not exceed 2359. It will be within 2359. Line sweep, maybe. Like, there are multiple ways to do similar problems, such problems, right? Again, let's understand this problem in a very trivial fashion. What is given to us? We are given for a train. Let's say this is a train, right? This is a train. What are we given? Can we create one array for one day? Yes. So we are given three things about a train: L, R, and D. L, R, and D. What is L? L is the arrival time. R is the departure time. D is the day. Okay. First of all, let's get rid of this third dimension altogether, right? So we are always concerned. We are always concerned about a single day. Yes, exactly, Santosh. Very good. We are always concerned about a single day. We are always concerned about a single day. So we can process all the D days. Whatever the number of days is, we can process each day separately. We can process. So what we'll do is we'll process each day separately. And again, why is that? Because the trains at day I, they will not be affecting the trains at day I plus 1. These are two independent events that are happening. They will not be affecting, because we are given a statement here that the trains should be living in the same format. Sorry, the train should be living in the same day. If the train, the train platforms you have, also each train arrives and departs on the same day. So no train of day I will be affecting the trains of day I plus 1. So we can just get rid of this D format and we can just process for each of the days independently, right? So process for each of the days separately. That's one thing to note. Now what do we have? Let's focus on one day. Let's focus on one of the days, right? So for one day we have trains where trains are represented like L, R, or arrival time, departure time. These are ranges, right? You are given, basically, let's say there are k trains that are coming today. So essentially you are given k ranges. You are given k ranges. So ranges means like this. This is a train. Let's say it comes at 1, it leaves at 5. Then you have another range. Let's say it comes at 3, leaves at 8. You have another range, comes at 8, leaves at 12. You have another range, comes at 10, leaves at 14. You have another range, comes at 11, leaves at 12, right? You can have multiple ranges like this. Now this makes the question much clearer, right? You are given a set of ranges. What you have to tell is, at any point of time, what is the maximum number of trains you can have? At any point of time, or at any point, what is the maximum number of trains that you can have? Okay, no, the number of platforms is, we don't have to maintain different platform. We'll understand what is the work of platform. Why do we need the platform? Because if you find this sorry, maximum number of trains at any point of time, for example, here, what is the maximum number of trains at any point of time? It will be 3, right? At 11 you have 3 trains. Now as we can have 3 trains at time 11, right? At time 11, as we have 3 trains, we would need 3 platforms, right? At time 11 we have 3 trains, we would need 3 platforms for them, right? Yes, activity selection, exactly. Let's say you are not allowed to do more than k activities. Now more than 2 activities. Now you see here that at this step, at 11, you have 3 activities lined up, so you cannot do them, right? So similarly, at time equals to 11, you have 3 trains lined up, so you cannot have them in 2 platforms. If you have 2 platforms, you cannot have 3 trains in 2 platforms, so your answer will be no. And if no point exists, your answer will be yes. So simple, right? Again, basically the problem now reduced. What has the problem reduced to? The problem has reduced to, given k ranges, find the maximum number of ranges that intersect at a point. Given k ranges, find the maximum number of ranges that intersect at a point, because that will mean at that time, at this point, whatever the point is, at this point, there is the maximum number of trains that are coming. If the maximum number of trains is greater than the number of platforms, the answer will be no. Otherwise it will be yes, right? So this is what we have reduced the problem to. Now how do we calculate this? Given k ranges, find the maximum number of ranges that intersect at a point. This is something we have discussed again in the last week. We had done a lot of range problems. ARR, L plus plus, ARR, R minus minus. In this case, it will be ARR, R minus minus, because if you see the problem statement again, it tells that if 2 trains arrive and depart at the same time, you can have them in a single platform. If 2 trains arrive and depart in the same time, you can have them in the single platform. That means you can actually, if you are given a range L to R for a train, you can actually think that the train stays in the platform from L to R minus 1. So r plus plus will become r plus 1 will become r. So we can do arr l plus plus arr r minus minus, and after that we'll do a cumulative sum. We'll do a cumulative sum, and we can tell that these many trains are, and we'll find what is the number of trains at any point, right? What is the maximum number of trains at any point? We can tell that. Now, those who didn't attend last, this is something we had discussed in the last class. Those who didn't attend, let's quickly discuss it again. Like how this helps us, arr l plus plus, arr r plus 1 minus minus. So basically, let's say you are given k ranges, right, of the form L to R. And let's say in this case, L and R both are inclusive. Yes, see some greater than number of platforms, return false. Exactly. So in this case, let's assume L and R both are inclusive. In our case, R was exclusive. R was exclusive. But in this case, let's assume L and R are both inclusive. So whenever you have such things, if you want to know at any point of time how many ranges are intersecting, or how many ranges are there at any point, or any point on the line, how many ranges are there, or anything like that, what you can do is you can follow a concept that is, let's say, let's consider a few ranges, right? Let's say 1 to 4, 2 to 6, 6 to 8, 7 to 10, 8 to 9. Let's say these are a few ranges that we have. So what I'm saying is, if you just do ARR, you take an array, you just do ARR L plus plus, ARR R minus minus, R plus 1 minus minus, ARR L plus plus, ARR R plus 1 minus minus, and you then take a cumulative sum. For every point, you will actually get the number of ranges that are crossing through that point. Let's understand. Let's draw this, right? ARR. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, and let's say 10. Initially everything is 0. Let's write them as well. So first it comes 1. So ARR 1 plus plus, so it will become 1. ARR 4 plus 1, that is 5, R plus 1, 4 plus 1, that is 5, minus minus. So it will become minus 1. It will become minus 1. Now 2 to 6, ARR 2 plus plus, so 2 will become plus 1. 6 will become 6 is 6 plus 1, that is 7. 7 will become minus 1. So 7 will become minus 1. 6 to 8, 6 plus plus, 6 plus plus, so 6 is becoming plus plus. 8 is becoming 8 plus 1, that is 9. 9 is becoming minus 1. 7 to 10, so 7 plus plus, 7 is what right now? 7 is minus 1 right now. Minus 1 plus 1 is 0. So 7 becomes 0 again. Let's cut it and write it up. 7 becomes 0 again. And 10. 10 plus 1 is 11. 11 minus, minus. So minus 1. Now we have 8, 9. 8 plus plus. So 8 is 0 right now. 8 becomes 1. And 9 plus 1, 10. 10 becomes minus 1. Now you take the cumulative sum. You take the cumulative sum and see what happens. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's take up to 10 only. So cumulative sum is, just take the running sum. See, so initially 0. So it will be 0 here. Now 0 plus 1 becomes 1. 1 plus 1 becomes 2. So C sum is 2 right now. At 3, we have 3 plus 0, that is, 0 plus 2, that is 2. We'll go to 4, 4 plus 0, that is 2 again. Minus 1, sorry, not 4, 0 plus 2, that is 2 again. At 5, we will have minus 1 plus 2, that is, it will become 1. So it will become 1. At 6, we will have 1 plus 1. We have 1 already here, plus 1 because of 6. So we'll have sorry, it will become 1 at 5. At 6 it will become 2 again. At 6 it will become 2 again. At 7 it is 0. So 0 plus 2, that is 2. Okay, 5. I've written this a bit wrong. Yeah. 5 it would have been 1. 6 it would have been 2. 7 it will remain 2. At 8 we have plus 1. So we'll add 1 to the cumulative sum. 2 plus 1, 3. And it will become 3. At 9 we have minus 1. So it will become 2 again. At 10 we have minus 1. So it will become 1. And at 11 it will become 0. Now see, at every point 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it will tell how many ranges are exactly passing through that point. Let's take an example. Let's say 8. We are saying that 3 ranges are passing through 8. Is it true? 1 range, 2 range, 3 range. So 3 ranges are passing through 8. Let's take another point. 4. We are saying 2 ranges are passing through 4. 1, 4 and 2, 6. 2 ranges are passing through 4. So at any point it will tell you how many ranges are passing through that point. So you can find this and you can just see what is the maximum out of here. The maximum or the C sum should never be greater than the number of platforms. As simple as that, right? So again, I hope that you guys can write the code yourself. This is very simple. And this is the logic, right? This is the entire logic, nothing else. Just process it for all the days. For each of the days, process it separately. And this should be the entire logic. Okay, so try to write the code for this. And if you have any problem with the code, just watch last week video, because there we had multiple similar problems. So I have discussed the code there, right? So that will be the code. Cool. Let's go to the last problem. Okay, let's go to the last problem. Good. Okay, let's see. So we are given night is at xy. So the problem name is night in Geekland. The problem statement is a bit big. To separate the arrival and the departure time for different days, we would need to create separate DS, right? Just create for each day, create a new array or something like that. So it will be a vector of vectors, right? A vector of vectors or an array of arrays. So just separate them like that, and that should work. Cool. So night is at xy. Night is at xy in Geekland, which is represented by a R cross C 2D matrix. Each cell in the matrix contains some point. In the ith step, the knight can collect all the points from all the cells that can be visited in exactly I steps without revisiting any cell. So what it tells is you are given Geekland. Okay, the pen has fallen. Yeah. Okay. So you are given the matrix for Geekland, where each cell has some value, right? Each cell has some value. What you have to do is the knight can collect. So the knight means it's a chessboard knight, right? So you know how a knight moves in a chessboard. It moves by 2 places in one direction and 1 places in perpendicular direction, right? So how does a knight move in the chessboard? Like this, right? You have the knight here. It will go 2 steps this side and 1 step this side, or 1 step this side, and the same thing here. 2, 1, 1, 2 steps this side, 1 step this side or this side, 2 step this side, 1 step this side, right? This is how the knight moves in the chessboard, right? 8 possible moves. Okay, so the knight will move in the chessboard. Now it is said that, or knight will move in the board. It says that each cell has some value. Each cell has some coins inside it. The number, so after at I steps, right? At I steps, so it tells that in the ith step, the knight can collect all the points from all the cells that can be visited in exactly I steps without revisiting any cell. So what it tells here is that, let's say this is the cell where the knight is. Now, after one step, he can come here, 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 here. These are all possible cells the knight can come in after one step without revisiting any cell. Now, for step I, the knight can collect all the points. That is, all you have to, for step I, you have to add all the values here. You have to add all the values, right? That it can visit. You have to collect all the values that it can visit. Right? So that is what is said here. In the ith step, the knight can collect all the points from all the cells that can be visited in exactly I steps without revisiting any cell. So all the cells you can visit after I steps, that number of coins in that cell will be added to the answer for step I. Again, we are not sure about what the final question is. Also, the knight has some magical powers and that enabled him to fetch the coins from the future. That is, if the knight can collect y coins at the xth step, he can fetch all the coins that he will collect in x plus yth step. And if the knight collects z coins from the yth step from here, he can fetch all the coins from the y plus zth step. Okay, this is a bit complicated. Let's understand this. Let's understand this in simple words, right? With some diagrams. So let's say, let's forget about the knight, right? Let's forget about the knight. Let's say from here, the knight can visit these cells in one step. In one step, the knight can visit these cells, right? Let's say the total number of coins, that he collects, these are all one step, right? So the total number of coins he can collect from one step is the summation of all of them. Let's say the summation of all of them comes to be 10. It tells that without, the knight can actually collect from, it has some special power, it can collect some coins from the future as well. And what are the coins? The number of coins that he can get from 10 steps from here. If he takes 10 steps from here, from each of them, whatever is the possible set of nodes that will be there, after 10 steps from here, whatever will be the possible set of after 10 steps from here, whatever will be the possible set of cells he can visit, whatever is the sum of these, right? That is, it is basically step I plus 10. At step I plus 10, he will be collecting these all. But instead of collecting these all at step I plus 10 or 1 plus 10, basically, that is 11. Instead of collecting them at step 11, he can collect them now only. Let's say the total sum here is, so we have the total sum here, let's say is 50. Let's say the total sum here at step 11 is 50. This is step 11, right? Now further, he can repeat this process. That is, now from here, whatever is 50 steps away, that is 61. Total number of steps will be from starting is 61. Whatever is 50 steps away from here. So let's say these are the nodes that are 50 steps away from here. He can collect those values as well. Just by making this first move, he can collect those values as well. That is steps of 61. Because 50 steps from 11, right? Not 50 steps from the starting, 50 steps from 11. Where he reaches all the cells, he can collect those values as well. And like that, this can continue infinitely, right? As long as he has not visited all the cells. Like, he cannot revisit a cell. Right? Or if we do not, just think about it in a linear fashion instead of multiple nodes. Let's say in one step, he reaches some cells and total number of coins he can collect is 20. Now from here, he will move to, from this point, he will move to all the cells that are at a distance of 20 and are not visited yet. That is the distance of 20 and not visited yet, and he will collect all the coins from there as well by using the special power. You do not have to travel. So what is the number of coins? Let's say the number of coins here is 50. So now from this point at a distance of 50, whatever cells are there, from there he can collect the coins, right? From there he can collect the coins again without actually making the move. Like from the future he's collecting the coins. So that is exactly what this tells, right? What this problem entirely tells. Okay, so let's read it again. Now with the diagram, let's read it again. So if the knight can collect y coins in the xth step, he can fetch all the coins that he will collect in the x plus yth step. And if the knight can collect z coins in the yth step, he can fetch all the coins he has collected from the y plus zth step, and so on without increasing the step count. That is, the knight will stay at the xth step and he will collect all the coins from the future steps, right? Find the minimum number of moves or steps the knight has to take to collect the maximum number of coins. So you have to tell what is the minimum number of moves the knight has to make to collect the maximum number of coins. That is the question, right? Okay, so take this as input. 9 10, we have the starting of the knight is at 4 5. So this is the starting point, right? This node marked with yellow is the starting point. So what are the nodes, what are the cells he can visit in one step? How does the knight move again? 2 steps up, 1 step to the right. So all the cells that are marked with red, these are the nodes or the cells the knight can move in 1 step. Verify that. Like 2 steps up, 1 step left, 2 step 1 up, 1 step right, 2 step right, 1 step up, 2 step right, 1 step down, 2 step down, 1 step left, 1 step right, 2 step left, 1 step up, 1 step down. So all the nodes marked in red is will be valid, right? Now here it tells that, see, at 0 the knight cannot collect anything. At 0 the knight cannot collect anything, so because there are 0 coins. So he cannot use the special power because 0 plus 0 is 0, right? So he cannot use the special power. So he will take 1 step. After 1 step, how many coins does the knight collect? After 1 step, he can collect the summation of these many coins. So 1 plus 0 plus 0 plus 0, whatever. So he can collect 1 coin. So the maximum, he will take 1 step to collect 1 point. So he collects 1 coin. Now from 1 coin, he can collect 1 plus 1. That is all the coins in the second step. All the coins in the second step will be the ones marked in green. The ones marked in green will be all the coins after second step. So whatever is that, whatever is the count, so that, and it will continue like that. Like let's say total count here is total count here is 64, right? 2 2 2, all of them are 2. So total count here is 64. Now from this he can move by 64 steps. From these cells, what will be the nodes he can visit after 64 stage, right? So that will be there 64 steps. So they will go, definitely they will not be within this, so we'll end here only, because the 64 steps after this will be outside, will not happen in the matrix. We would have visited the entire matrix. 64 step would not be possible, so we'll stop it here, and we can tell that just by taking 1 step we get the maximum answer, right? So the output is 1. Okay, let's look into the second example. The second example is 768 914 628. Let's understand this. 768 914 628. 768 914 628. Okay. 768 914 628. Now the rook starts from, let's say, here. The rook starts from here. So without taking any step, the rook can collect 1 coin. So now as the rook can collect 1 coin, he can use the power to collect all the coins at a step at which are at a distance of 0 plus 1. 0 because it is standing here. right now 0 steps are taken. So 0 plus 1, that is all the nodes at a distance, all the cells at a distance of 1, he can collect those coins. So what are the nodes at a distance of 1? So it will be 7, 8, 6, 8. So these many coins he can collect. Now whatever is the number of coins from these points, he can move up to that many distances to collect the remaining coins. So eventually he'll take up these as well, because this will be much more, like 7 plus 8 plus 8 plus 6 definitely will be much more than the moves needed to reach 9, 4, 6 and 2, right? So the answer for us will be, with 0 steps he can collect all the coins. With 0 steps he can collect all the coins. So that will be the answer, right? Okay, so that is okay. Yeah, so this is the question. We have to tell how many minimum number of steps is needed. Actually, the problem statement is very complicated, right? The problem statement looks very complicated, but the problem is very simple. Why? What do we have to find? First thing we have to find is sum of all the coins at distance I for each I. Sum of all the coins at distance I from each I. Is this trivial? Is this trivial to be done? Yes, it is. Why? We can just do a BFS. We can just do a BFS and we can mark what is the distance, what is the minimum time taken, or what is the distance of each node from the source. We can mark for each node what is the distance of, let's call ij, is the distance from the source. Now we can maintain an array, let's call it a sum array. We can just do like this: sum of distance of ij plus equals to the number of coins in ij. And in this way we find the sum of all the coins, at a distance I. This way we can find the sum of all the coins at a distance I, right? For example, okay, for example, let's go to the example again. Here at distance 1, what are the nodes? This 1, 1, 0, 0. So they will have a distance of 1. So in the sum, what will their distance be? 1. So in sum of 1 plus equals to, what will do? Sum of 1 plus equals to 1. Sum of 1 plus equals to 0. Sum of 1 plus equals to 0, like that. So what is the next sum we'll get after one step? We'll get 1. So like that, for all the distances, we'll calculate this. We'll get the sum properly. Similarly, for two distances, distance of 2. These all will have a distance of 2. So what we'll do? Sum of 2 plus equals to 2. Sum of 2 plus equals to 2. Sum of 2 plus equals to 2. So we'll be ending up with 64 values. We'll end up with 64. Okay. So this is the first part, right? This is the first part, that is, we'll find the sum of all the coins at distance I. Now, how about the power? We also have a special power to collect from the future, right? And that is simple, right? Because once we have sum I is what? Sum I is the number of coins we can collect at ith step. Number of coins we can collect at ith step, sum of I is that. But we are also saying that sum of I is number of coins we can collect is not just this, but it is also equals to sum of I plus equals to the number of coins we can collect from I plus sum of I. We can run a reverse loop and calculate this, because at ith step, if we get k coins, we can use the power to get all the coins that we collect at I plus kth step as well. So that's exactly, at ith step we are getting sum of I number of coins. So at ith step only we can use the power and get sum of I plus sum of I, and sum of I plus sum of I will have computed the sum of I, like this value, sum of I plus sum of this thing, let's call it k k plus sum of k, it would have calculated this value as well, right? So like this we can do, and then we can just loop and check for which I it will be the maximum, right? So there is nothing actually very complicated about this question. That's exactly what we have to do. Again, the code will the problem the what the logic will become much clearer once we write the code for this. So let's actually go ahead and write the code because it's very simple, right? So we'll just directly write the code for this. Okay, so we'll have to do a BFS. Let's mark the distances. So distance of nm initially, and we'll fill them I less than n I plus plus, j equals to 0, j less than m, j plus plus, distance of ij equals to, let's say initially we fill up with a bigger value, let's call it n into m. Yeah, maybe something like this, n into m plus 1. Okay, so after that, start x, start y. So what we'll do here is, first of all we'll do a BFS, right? So BFS, that is distance. Also start x, start y is 1 based or 0 based. Let's see that. 2D array means step, start x, start y will be 4 5. So 4 is 0 based. Okay, it is 0 based. So distance of start x, start y equals to 0, right? Distance of start x, start y is equals to 0. All right, so okay, what we'll do is after this, uh okay, so what we'll do here is, it is 0, and we'll also have a q int q, and q dot push, actually pair int int will have two values, pair int int, and q dot push will push start x, start y. All right, and vector int is the number of coins, I believe. Yes, it will be the number of coins. So we'll also maintain vector int distance. Okay, let's first calculate the distances. So for int, for while not q dot empty, while not q dot empty, and we have to maintain the directions as well, right? For DFS we have to maintain the directions as well. So int dx equals to, what are the moves we can make? We can make +2, -2, 2 plus 1. So 2 plus 1, 2, minus 1, 1 2, minus 1 2, 1 minus 2, minus 1 minus 2, 2 plus 1, 2 minus 1, minus 2, minus 2. 8 values are there. 1 2 3 4 5 6 7 8. 8 values are there, right? So int dy equals to 2 1, 2 minus 1, 1 2, 1 minus 2, 1 1 2, 1 minus minus 1 minus 2, 1 minus 2, minus 1 2, and minus 2 1, minus 2 minus 1. I think all of them are unique. Let's see, 2 1 is there, 2 minus 1, 1 2, minus 1 minus 2, 1 minus 2, minus 1 2, minus 2 1, minus 2 minus 1. Yeah, so this should be the number of moves. So what we can do is, yeah, while not q dot empty, and we'll get the pair. So pair int int p equals to q dot front and q dot pop. Right now, we will go through all possible next nodes. So for int I equals to 0, I less than 8, I plus plus, int next row equals to, yeah, next row equals to what? Int next row equals to q sorry, p dot first, that is the row, p dot first plus dx of I. In next column, again this is a simple BFS on matrix code that I'm writing. If anyone is confused about this, dy of I, right? Next row, next column is p first plus dx, p plus second plus this. Now we'll check if the cell is valid. So how will the cell be valid if next row is greater than equal to 0 and next row is less than n, and next column is greater than equal to 0 and next column is less than m, and distance next row. Okay, if it is a valid cell, let's add it inside. If this is a valid cell, in that case, if the distance is less, right, if distance of next row, sorry, next row and next column is greater than distance of the current distance of p dot first, p dot second plus 1, we'll update the distance first. So let's copy this part. Distance of this and this will be equal to, we'll update the distance, we will add it to the queue. So q dot push next row next column. So that should be it for finding the distance of each of the nodes. So we have completed the BFS. Now what we'll find is, we'll find the maximum distance. Let's call it n. Y plus 1, because we are taking one step here, right? We are at p. Now we are going to all possible next cells. So this is the distance of p, but we are taking one step to go to the next row next column, right? So that's why plus 1, distance of this plus 1, right? So we'll find the maximum distance. Let's initialize this with distance of 0 0, distance of 0 0, and for int I equals to 0, I less than n I plus plus, for int j equals to 0, j less than m j plus plus, n equals to max of n or the distance of ij. So we are finding the max distance possible. Why do we need that? Because for each distance we have to maintain an array, so we'll have to create the array of certain size, right? So now we can create the array of distances, sum of size n, n plus 1 rather. Let's do n plus plus here, n plus 1 we can then do. So n plus plus and n will create some array of n, right? So initially everything will be 0, so let's initialize this with 0. And now for, or we can just do fill as well. So fill also works. Fill sum plus n and 0. Now we'll go through all the cells again. We'll go through all the cells and we'll add to the sum, right? So sum of distance of ij plus equals to the number of coins at that cell, a of ij, right? So now for int I equals to n minus 1, I greater than equal to 0, I minus, we also have to update, like this will contain, now the sum contains sum of I will contain all the sum of the coins at distance of I. but we can use the power to get I plus sum of I as well, right? So that is what we'll compute now. So sum of I, if I plus sum of I is less than n, in that case sum of I plus equals to sum of I plus sum of I. So this is, will now we have in sum of I all the, after I steps, what is the total number of coins we can collect, including after using power, right? So now we'll just have to return the minimum one. So for int I equals to 0, I less than n, I plus plus. So int max equals to sum of 0, and let's call it max e, and int answer equals to 0. We'll start from 1. If sum of I greater than max e equals to sum of I, and answer equals to I. Finally we can return the answer. So return answer. So that should be the code, right? Again, the main challenge was here writing the DFS. After we have done the BFS, it's pretty simple, right? Just we have to, although the problem statement is a bit complicated, like it explains it in a difficult fashion, but it's not exactly complicated. It's just that you have to calculate it backwards using similar to prefix sum or similar to DP that you have done, right? So let's submit this now. Okay, we got a wrong answer. Our code's output is 19 for some reason, and its correct answer is 2. So yes, it should not go to 19. Not sure why it has gone to 19. Can you explain line 73? Yes, sure. So we have to give the answer, like we have to tell what is the minimum number of steps at which we can collect that we have to take to collect the maximum number of coins, right? So that is, we are going through all possible number of steps. Like step 1, we can collect all the coins at distance 1 plus all the coins at distance like I plus sum of I. Similarly, at step 2, we can collect all the coins at distance of 2 and the corresponding sum, right? So yeah, that's what it tells here, that that's what it tells here, that sum of I, yeah, so we are finding, like we're going through all 1 to n, and we are finding what is the maximum number of coins that we can collect. So sum of I is greater than the max element, like we are basically finding in this sum array at which point we have the maximum, which index we have the maximum, right? So that's there. Let's see what we have done wrong. So we have done all possible moves, right? We have done all possible moves here. 2 1. Let's actually yeah, 2 1. Yeah, so what I'll do here is I'll just open this and move to, yeah, let's see if we have done all possible moves, right? So 2 1, 2 1 means row is plus 2, row is plus 2, that is downwards. We have the color of white, we'll take it red, plus 2, and then plus 1 on column, that is right. So we'll reach here. 2 minus 1 will go 2 and will come minus 1. 1 2. So we are going uh 1 2. No, 1 2 is not valid, right? So 2 1, I think that is the mistake. 2 1, 2 minus 1, then we should have come to this and this and this and this. Okay, so this is 2 1, 2 minus 1. This is Yeah, I think this is 1 2 only, right? This is 1 and uh, plus 1, and for column, for row it is plus 1, and for column it is plus 2, and this is minus 1 2, 1 2 and minus 1. So this is done 1 2 and minus 1 2, this one. Now this one is row 1 column minus 2, 1 minus 2. So 1 minus 2 will be somewhere here, 1 minus 2, yes. And I think the mistake, we are using dx with row and dy with column on line 34 and 35. uh, that's the purpose, right? Like dx d, it should be d row, but yeah, like it should be with row only, right? uh, let's call it, instead of dx we can call it d row. Not exactly x axis y axis, it's x was into like work with row and column, right? So row and column, cool. So let's actually write all the values here. So 1 minus 2, and this will be minus 1 and minus 2. This will be minus 2 1, minus 2 minus 1. Let's see all of them are there or not. So 2 1, 2 2 1 is, this one is 2 1, and this is 2 minus 1. So 2 1 is there, 2 minus 1 is there, 1 2, 1 2 is there, minus 1 minus 2, it is also there, 1 minus 2, 1 minus 2 is also there, minus 1 2, minus 1 2 is also there, 2 minus 1, 2 minus 1 is there. So 2 minus 1 is minus 2 1, sorry, it's minus 2 1, minus 2 1 is there, and minus 2 minus 1 is also there. So I think all of them are there. 1 2 is also there, 1 minus 1 2 is also there, right? Yeah, so I think dx and dy is correct. This part is correct, hopefully. Okay, let's see what we have done, what we might have done wrong. So next row is greater than equal to 0, next column is less than n, I less than 8. So there are 8 moves, 1 2 3 4 5 6 7 8. There should be a loop in the distance update section. Which one? Why will there be a loop? Distance of next row next column is greater than distance of p dot first. We are initializing the distance as well, right, with n into m plus 1. So and nm are within 10 to the power 3, I believe. Yeah, within 10 to the power 3. So no, that should be okay. N into m plus 1. Static is the row, start y is the column. Okay, static is the row or the column? Let's see. 4. So 4 means 0 1 2 3 4. It is indeed the row. And 5 0 1 2 3 4 5. So it is the column, right? So static start y is also correct. This and q dot front I less than 8, next row p dot first plus d column of I, next row equals greater than equals 0, next row less than n, next column something on line 70. Okay, line 70 max equals to sum of 0. We are updating the sum, right? And max equals to sum, if sum of I is greater than the max element we have found till now, so max element equals to sum of I and answer plus equals to I. Okay, also we have done fill sum of n. So let's actually print the sum of n, right? For int I equals to 0, I less than n, I plus plus, C out sum of I, and C out endl. Let's print it up and we'll run on this test case only where it failed. Okay, let's submit this and see where it fails. Yeah, let's see if it runs correctly. Loop at 64. So there is a loop, right? I plus sum of I is less than n. Sum of I plus equals to sum of I plus sum of I. That's the loop, right? 8, 15, 34, 37, 13. Our answer is 3 for some 0, 1, 2, 3, 37. Okay, answer is 3. Expected is 3. That's fine. Let's remove this and find which test case it failed so that we can run on that directly. Somehow it is getting up to 19 steps. Let's see. Yeah. Okay, 47980000, and after that suddenly 83 at 19 steps, right? Uh, let's print the distance array. Let's Yeah, let's print the distance array as well. So for int I equals to 0, I less than n, I plus, sorry, I equals to 0, I less than n, I plus plus. For int j equals to 0, j less than m, j plus plus. Cout distance of ij, cout end. Yeah, let's now run this. Okay, we have many nodes that are being visited at distance of 19, right? ऐसा क्यों आ रहा है 19 डिस्टेंस क्यों आ रहा है? समथिंग इज रॉन्ग विद आवर डीएफएस. ओके, एक सेकेंड. 19 19 19. हाँ, काफ़ी nodes are visited after 19 steps for some reason. That should not have been the case. Let's see. uh, okay. 19 1 19 19. Where are we starting at? We are starting at 2 9 and we have 1 1. We are starting at 1 1 0 0 1 1. We are starting at this point, right? So to reach this point, how many moves will it take? So in one move it can reach uh 1 2 3. It can reach here. Where is 4? 4 is not even there. After that सभी 19 है. They are not reachable. Okay, okay, there might be points that are not reachable as well. That's good to know. So okay, I think it is n into m, right? I think the this is basically n into m, so we should just ignore that, right? So and distance, sorry, let's just ignore n into m. So we'll have to just add some additional code for that. So here max of distance I if distance of ij, or let's keep it as int max, right? Let's keep it as int max instead of this. And what we'll do is here we have to just be a bit careful that if distance of ij equals to int max, then continue. Then continue, and here also otherwise n, and here also if distance of ij equals to int max. In that case, continue. Otherwise, do the sum and then find the sum. Okay, let's run this now. That should ideally work. Let's see. So now, okay, run. Somewhere I'm accessing this memory. So let's see where I am. Distance of ij. Cool. Let's remove this. N equals to distance 0, 0. That cannot be possible actually. N equals to 0. Let's do it. Right. So max of this n plus plus sum of n. If this, and yes, that should be there. Let's run this now. Okay, we have the answer to be 2, which is true, right? So we just have to remove this print statements, and now let's run this. We'll compile against this as well once. Yeah, the initial, those nodes are never visited, so that's why 2 2. So let's submit this now. Yeah, so this code is working, so that's the logic. I hope this makes sense, right? So yeah, we are done with all the problems. Let me know if you have any doubts, otherwise we can call it a day. Anyone has any doubts with the approach? Vasant, we are actually, why are we using Intmax? Yes. So I have made this Intmax because again, like I have to write the condition n into m plus 1 everywhere. So that's why I have made it Intmax, right? It's easier to write equals to Intmax than n into m plus 1. Vasant, not really. This actually gives us the ultimate maximum, ultimate sum, because if you see, we are calculating it backwards. So already for sum of I plus sum of I, the corresponding sum is also calculated already, right? So it's dp. What we are doing here is basically dp. So that's why we do not need to compute it again. So I hope this makes sense. Cool. If you have no more doubts, then thank you for joining in. And yeah, I'll be seeing you in the next class. That is next week, right? So thanks and good night.